Hello. In this video, we will cover section 6.1, which is on probability distributions. A probability distribution presents the outcomes of an event or experiment, along with the probabilities that are associated with those outcomes. For example, the probability distribution when rolling a single die would be as follows. So you've got the 6 possible outcomes that you can get with a single die. So you can have anywhere from 1 to 6 pips showing, depending upon what face ends up coming up. And then there's a 1 in 6 chance of each of those occurring. And so that's the probability for each of those. And so we also have to note that when it comes to probability distributions, the sum of the probabilities must always be 1. Here's an example with 2 dice where we go through and add up the number of pips that are showing. So we can have anywhere from a 2, which would be 1 pip on each die, up to a 12, which is where we would have 6 pips on each die. Now, the probability is not consistent this time, and that's because there are multiple ways that we can get some of these outcomes anyway. So there's only one way to get 2 pips. Again, that's 1 on each die. But there are 2 ways to get 3 pips. So you could have 1 on the first die, 2 on the second, or 2 on the first die and 1 on the second. Okay, and the sum, again, always must be 1. All right, let's look at a non-dice example. So suppose a playlist on your MP3 player has 10 songs. 6 are rock, 2 are country, 1 is hip hop, and 1 is opera. You put your player on shuffle. What is the probability that the first song played is rock? All right, so the probability distribution that would be associated with that is below. So we can see we've got rock on there, and then there are 6 out of 10 songs that are rock. So that gives us a 6 in 10 probability. And then not rock would be the rest. So 4 out of 10. And again, if you added these up, you'd get 1. All right, so let's look at discrete versus continuous variables. This is going to matter throughout the rest of the chapter because we're going to look at different sections. And one section is going to cover discrete probability distributions, and one is going to cover continuous probability distributions. So we'll start with discrete data. Discrete data is countable. There are finite possible outcomes. Outcomes are typically integers, so that's whole numbers, negative and positive versions. The outcomes can all be listed, even if it would take a long time. So some examples of that, example would be rolling a die. As we've seen, there are 6 possible outcomes. If you can list the outcomes, then that's discrete. If you rolled 2 die, there are 11 possible outcomes. Again, we can list them, so that's discrete. Picking a card from a deck, 52 outcomes, again, listable. And then I added phone numbers here to illustrate that it would take a very long time to list all the phone numbers, but you could do it. There are a finite number of phone numbers. There's not infinite. And if you sat down and wrote all of them out, it would take you probably thousands of years, but you could list all of them. And so if you can list it, then it's discrete. Continuous data, by contrast, is uncountable. There are infinite possible outcomes. All right, how do we represent that? Outcomes are typically fractions or decimals. And because of that, you could not list all of the outcomes. So what are examples? Anything that you'd use decimals with is going to be an example. So weights, we would use decimals with. Height, time, temperature, revenue, or profit. Okay, and so the reason that these are uncountable and the reason that there are infinite number of outcomes is that with decimals, you can always add more decimal places. So if you were studying something and you had 20 pounds, for example, you could do 20.01 pounds would be kind of a neighbor to 20 pounds. And then if that weren't enough of a small enough increment, you could do 20.0001 pounds or 20.00000001 pounds. You could always add more decimal places to come up with more outcomes that are, kind of within a very narrow range. And because of that, because there's no limit to how many decimal places you can add, that makes it so there's no limit to how many outcomes that you could have. And with infinite data, you end up with so when we think of infinite data, we think of continuous data. And so the two, discrete versus continuous, are going to behave somewhat differently. And so we do want to be able to understand what what the differences are that define them. Okay, so let's look at some examples just to make sure that we understand the differences. So let's see, the weight of a submarine sandwich you're served at a deli, would that be a continuous or a discrete variable? The elapsed time from when you left your house to when you arrived to class in the morning, the number of people in the next passing car, the blood alcohol level of a driver, and then the number of eggs. So again, what you want to think about when you're looking at these are, do you use decimals, or is it countable? Like those are really the two things that focus your attention on which one is which. So with weight, the weight of a submarine sandwich, that would be an example of a continuous variable because we use decimals with weight. Elapsed time, so time we also use decimal, right? So you could have 10 minutes and then 10.01 minutes and 10.00000001 minutes. And so we could add as many decimal points as we want when it comes to time. And so that is infinite data. That's going to be an example of continuous. Number of people in the passing car. People is countable, not infinite. There's not infinite people in the car. And so we would say that's discrete. The blood alcohol level. So blood alcohol level, I believe, is a percentage. But regardless, we use decimals with it. If you go and just Google blood alcohol level, you'll see it's point something. And as soon as you have decimals, you have continuous data. And then the number of eggs laid. So we don't have decimals with eggs. Eggs would be countable. Even if a salmon had a lot of eggs, which perhaps it does. I think some fish have thousands of eggs, lay thousands of eggs. It's still countable. You still have egg 1, egg 2, egg 3, and you get to the end and you'd have egg, whatever, 1,000. Okay, so no decimal points with eggs. And you can see I've gone and just put those answers, filled those answers in that we just went over. All right, homework. So this is a homework example. So there's more of these in the homework. And so let's go over these. So we've got the weight of a bunch of bananas, the number of people at a concert, the length of time to run a marathon, and the number of socks in a drawer. So again, weight, that's something we use decimals with. That's continuous. Number of people at a concert. We don't have half people or tenths of a person. We don't have 0.001 person. You have whole number of people, and you could go and count them. You could maybe by the ticket number that's on their ticket. So there's a listable number of people. So this is discrete. Length of time, you use decimals. So this is going to be continuous. And then the number of socks in a drawer, that's countable. You could lay out socks and cut them up. And so that's going to be discrete. Okay, so let's look at each different example of probability distributions. Let's look at discrete and continuous and discuss the differences. So discrete probability distribution can be represented using a table or a graph. When you use a table, you list all of the outcomes and the probability associated with that outcome. That may sound familiar. That's exactly what we were doing at the beginning of this section. We were listing discrete probability distribution tables. Another way that we did not do at the beginning of the section was to graph. You can go through and graph discrete probability distributions. The way that you do it is you put outcomes on one axis, probabilities on the other, and then you use a line segment to visually represent the probability. The taller the line, the higher the probability. So let's look at some examples. So we've got a statistics class at the University of California at Los Angeles, 40% male, 60% female. What's the probability distribution for this? Okay, so you can see we've got some coding, right? Remember that from back earlier in the course. So if you get a 0, that means false. A 1, that means true. So if you've got a column labeled female and you've got a 0, then that's going to stand for male. So for males, we have 40.4, which is 40%. And then for females, we have 0.6, which is 60%. Notice these add up to 1. Okay, that always has to be true with probability distributions. And then finally, we have our first example of a graph. The way that you do a graph, you put the outcomes on one axis, you've got probabilities on the other, and you do line segments, and the height of the line segment represents visually the size of the probability, the size in terms of the number, right? So 0.6 is 50% larger than 0.4. And so the difference between these lines, if you put them next to each other, is that this one should be 50% longer. Okay, so higher probability, longer line. Let's look at some more examples. So we've got Lincoln in the Bardo by George Saunders has received 1,477 reviews on Amazon. The reviews range in rating from 1 to 5 stars. And then so they want us to do, or they're showing us a probability distribution. So what does the probability distribution look like? So you've got from 1 to 5 stars. and then the probability calculation, from the actual reviews themselves. So 44% of the reviews are 5 stars, 15% are 4, 10% are 3, 11% are 2, and 20% are 1. Okay, and if you add those up, you should get 1. All right, to do the graph, you put the outcomes on one axis and you put the probabilities on the other. And again, the length of the line segments here represents the relative size of the probabilities. So if you look at 44 versus 15, 44 is roughly 3 times 15. So the length of this line should be 3 times the length of this line. Okay, that's how the graph should work. All right, and then we've got another one here. Roll a 6-sided die, you win $4 if you get a 5 or a 6, you lose $5 if you get a 1, and for the other outcomes, you break even. Okay, and so here we've got the table, the outcomes are on one side, and the probability of each outcome on the other. So losing 5, that comes from rolling a 1. There's only one way to do that in 6 when rolling a die. And then making $4, that's a 5 or a 6, so that's 2 out of 6 or 1 out of 3 when rolling a die. And then the other outcomes, so what are we talking about the other outcomes? Well, we've got 5 or 6 are taken up by the $4. 1 is taken up by the lose 5. So that leaves 3 left for where you break even. And those 3 out of 6 reduces to 1/2. So that's why the 1/2 is there. And we've got our graph that has the outcomes on one axis, probabilities on the other. And so for -5, 0, and 4, those are should be the relative sizes of the probabilities. This one should be roughly 3 times the size of this one, and so on. All right, so we've got a homework example. When a coin is flipped, the probability of it landing heads is 0.5, and the probability of it landing tails is also 0.5. If a coin is flipped twice, the different possible arrangements would be heads and heads, heads and tails, tails and heads, and tails and tails. And the probability distribution is shown here at the bottom. So it wants us to go through and find the probability of getting 0 heads, 1 head, or 2 heads, and then to make a probability distribution graph for that result. Okay, so we can go through and come up with the answer to that just by looking at our probability distribution here. So 0 heads, which one has 0 heads? That would be this one. There's only one of those, right? All these other ones do have heads. So we only have one case where we get 0 heads. And so the probability of getting 0 heads is going to be the probability that's listed there. That's going to be 0.25 or 25%. 1 head, so we've got 2 different results with 1 head. All right, so the combination of those are going to be the probability of getting 1 head. So 0.25 and 0.25 is 0.5 or 50%. So there's going to be a 50% probability of getting 1 head. And then finally, 2 heads also has a 25% probability, just like 0 heads did. And then the probability distribution graph we'll just do on the next table. All right, so 0 heads, 25%, 1 head, 50%, 2 heads, 25%. And then in a graph version of that would look like this. You've got the outcomes on one axis, the probabilities on the other, and the heights should be the relative sizes of these numbers. Okay, the middle one is twice the other two, so it should be twice as tall, which it does look to be. And then that's it. Okay, that's the answer. Okay, so let's move on. So continuous probability distribution. So what are the differences between discrete and continuous? A continuous probability distribution can only be represented using a graph, no tables. Okay, so no tables for continuous probability distributions. The reason for that is the infinite possible outcomes. It's not possible to go through and list all of the outcomes in a table when there are an infinite number of them. That kind of makes sense. The graph of a continuous probability distribution still has outcomes on one axis, but the other has the density of probability rather than the probability itself. Higher density means more probability. A curve is used to visually represent the density of probability across a range of outcomes. The places where the curve is taller have a higher proportion of the total probability than the places where the graph is shorter. Okay, so that may seem confusing, right? So density, what's that doing all of a sudden in here? So the idea of density is complicated, but it just means that the tall parts of the graph are where there's more probability and the short parts of the graph are where there is less. For example, if we go through and we look at this image, There's more probability around 2 than there is around 4 or 5, and that's the height, right? So the graph is tallest around 2, so that's going to be more probability there. The graph is short around 0 and 5, so there's going to be less probability there. What does that mean? It means that a person arriving at a coffee shop has a high probability of waiting around 2 minutes. It's going to have a high probability of waiting where the graph is tallest. That's going to be where the probability is highest. Okay, and they're going to have less probability of waiting the places where the graph is short. So less probability that you just walk in and immediately get served, or that you end up having to wait 5 minutes, the longest period of time in the graph. Density of probability is not the same thing as actual probability. So we don't go through and find the probability at 2 in this image. So you don't go through and say, what's the probability of waiting exactly 2 minutes? And then just kind of plug this in like it's a function, if you think about intermediate algebra. No, that's not how it works. What we do instead with density of probability is we find the probability by adding up across a range of values to find the area under the curve. Now, the idea of area under the curve, just like the idea of density, is quite complicated. But it just means that we find probability by shading a piece of the graph. All right. So, for example, in this case, that we would find the probability of waiting between 0 and 2 minutes by going through and finding the area under the curve between 0 and 2 minutes. And that's the only thing that you need to know at this point, is just that area under the curve ends up equaling probability. It's just something to memorize, really. All right, so the consequence of this result is that if you have more shaded area, then that means more probability. If you have less shaded area, then that means less probability. Okay, hopefully that makes sense. As with all probability distributions, the total probability needs to be 1. So the total amount of area under the curve is 1. So if we went through and found the probability of waiting between 0 and 5 minutes that's represented in this image, that's going to be 1. That's going to be the total of all the different possibilities. When you put those two together, if we can estimate the amount of area that's shaded, then we can estimate the probability, right? So if we know that the total is 1, then all we have to do is just try and eyeball what proportion of the total is shaded, and that's going to be the probability of getting that outcome. For example, if you look at this orange region here, it's about 45% of the total. How can you tell that just by looking at it? Well, just imagine if this were symmetric. If this were symmetric, the curve would kind of bend down and end here, okay, somewhere, like it would kind of look like that. And then you'd have half and half. And so if you just kind of draw a little line down here, you notice there's a bunch more white. And so since there's a bunch more white, that means there's more white than there is orange. And it's, I say a bunch more, like it's a lot, but it's not very much. It's only a little bit. And so it looks like it's close to, the orange is close to half, but just a smidge under because of that little bit of white that's left. And so that's where the 45% comes in. Okay, but again, so if you do probability, if you link probability with the amount of shade, and the amount of shade is 45% of the total, then that means that the probability is 45%. So if you put all that together, a person who arrives at the coffee shop at a random time has a 45% chance of waiting from 0 to 2 minutes. That's what you need to be able to get out of looking at one of these curves. Let's look at some examples to try and illustrate that. All right, so suppose that a bus that runs near the home of one of the authors arrives every 12 minutes. If the author arrives at a random time, the probability distribution is shown in the image. Okay, so in the previous slides, we talked about probability, a density curve, and this time it's a line. That's just the vernacular. So we still call lines curves. Anything that represents the probability is still treated as a curve, even if it's a line. The curve is a flat line. So the reason it's a flat line and not a curve is that there's an equal chance that the author would have any given waiting time. Okay, there's one waiting time is not more likely than the other. The nice thing about this example is that we can actually calculate the area under the curve instead of having to guess the proportion of the total like we did on the last example. And then they ask us to go through and actually find a probability by going through and find the probability that the author would wait between 4 and 10 minutes. So how do we do that? All right, so to find the probability the author would wait between 4 and 10 minutes, we need to find the area under the curve between 4 and 10. So we go through and shade that piece. Okay, and then to find the area that's given here, we can go through and use the rectangle formula. All right, so what is the rectangle formula? It says the area is equal to base times height. So the base of the rectangle is going to be this piece here that goes from 4 to 10. From 4 to 10, that's going to be 6 units long. You can get that by subtraction. 10 minus 4 is 6. And then the height is going to be the distance from, this line here that's at 0 up to the top of the top of our shape here. That's not labeled here, but it's labeled on the previous slide. So if you go back to the previous slide, it is 0.08333. Okay, so just filling that in. So that's the height. And then if you've got base and height, you can multiply them to get area. So 6 times 0.0833 is 0.5. And so thus the probability is 0.5. Okay. Now, another way to do this would be using the example that we just looked at, where we tried to estimate the proportion of the total that the shade represented. If you just took this and slid it over, that would basically be taking this white bar and putting it over here. You can kind of see that the red shaded piece is about half of the total. And so you could figure this out without even doing any calculations by just using the same method as we did on the previous problem, where you're guessing the proportion of the total. Let's look at another one. So Brian wants to go skiing tomorrow, but not unless there's between 2 and 4 inches of new snow. According to the weather report, any amount of new snow between 1 inch and 5 inches is equally likely. Again, we got that if there's an equal likelihood of any given outcome, then that's going to be a flat line for our curve. The probability distribution for tomorrow's new snow depth is shown. Find the probability that the new snow depth will be within Brian's ideal range. And then it wants us to shade the graph for the appropriate region. All right, so before we jump to the next slide, what should we do here? So we want to go through and find probability by using our curve here. To do that, you need to go through and find the area under the curve. Now, what area would we be trying to find? All right, well, we'll need to read the problem. It's going to be between 2 and 4 inches. So we want to go from 2 to 4 inches. So we want to shade that region. All right, 2 to 4 inches. Now we want to find the area of that. Now, conveniently, that's a rectangle. So we can use base times height. All right, what would the base be? The base would go from 2 to 4. All right, so that's going to be 2. What would the height be? The height's going to go from 0 up to where the top line is here, and that's at 0.25. So we're going to have 2 times 0.25. 2 times 0.25 is 0.5, or 50%. So what's the probability that Brian will get to go skiing tomorrow? 50%. Let's see all that written out. All right, so area under the curve is the probability. That's what we just said. We go through and shade that part of the curve, and that's going to be from 2 to 4. That's what Brian said he wanted. And it goes all the way from the bottom to the top. We can use the area formula, base times height. The base is from 2 to 4, that's 2 inches. The height goes from 0 to the top bar here, which is 0.25. Multiply those, and you get 0.5. And then you could say, thus, the probability of Brian being able to go is 50%. Now, just like the last one and the one before it, we could go through and look at this and, without doing any calculations, just try and estimate the proportion of the total graph that's shaded. And if we did that, that would also be a way to calculate the probability. Again, if you just kind of took this piece and maybe replace and slid it, or well, I guess took the green stuff and slid it over, or took this piece and put it here, you could kind of see that the green stuff is half of the total. And so the probability is going to be 50% without even needing to do any calculations. Okay, that is the video. Thank you for watching. I'll see you next time. Bye-bye.